Welcome, everyone, to today's Explainer. I'm stepping into the professor role today to take you through a story that starts out pretty terrifying, but actually ends up being one of the most inspiring things humanity has ever pulled off. I want you to imagine just walking outside on a gorgeous, sunny day. You feel the warmth on your skin, right? Well, what if I told you that exact same sunlight contains a type of radiation that can permanently damage your DNA? Radiation that can cause blindness, trigger cancer, and completely devastate entire ecosystems? Honestly, that is the reality we live in. But we are protected by this incredibly thin, completely invisible atmospheric shield. Now, about 40 years ago, we kind of accidentally started destroying it, but here is the amazing twist. Humanity actually came together and solved the problem. Okay, let's dive into exactly how we did that. Here are today's lecture objectives. First, we'll establish our invisible sunscreen shield. Then, we'll look at the miracle chemical threat, followed by the severe consequences of depletion. After that, we'll cover the unprecedented global solution, the massive climate co-benefit we gained, and finally, a quick summary on solving global problems. All right, let's jump straight into section 1, our invisible sunscreen shield. So to really understand this, we need to establish our atmospheric baseline. The atmosphere isn't just one big uniform bubble of air. It's distinctly layered. The absolute lowest layer, going from the ground up to about 11 kilometers, is the troposphere. That's the air we're breathing right now, and it's where our commercial planes fly. But if you go just above that, stretching from 11 to 50 kilometers up, you enter the stratosphere. And this upper layer is exactly where our entire story takes place today. Now, inside that stratosphere is a region packed with a higher concentration of a very special molecule called ozone. You see, the regular oxygen we breathe to survive is made of 2 oxygen atoms, but ozone is composed of 3 oxygen atoms, O3. And that unique chemical structure does something incredible. It basically acts as a giant's invisible sunscreen for the entire planet. It actively absorbs the sun's harmful UVB radiation, literally catching those powerful rays before they can reach the surface and permanently damage our DNA. But I want to share a totally shocking fact about this massive defensive barrier. If you were to take all of the ozone scattered throughout the stratosphere and bring it all the way down to sea level, squishing it under standard atmospheric pressure, the entire ozone layer would be a grand total of 3 millimeters thick. That's it. So the absolute crucial point to remember here is just how incredibly fragile the system is. Those are arguably the most important 3 millimeters on Earth, because without them, life as we know it simply wouldn't exist. Moving right along to section 2, the miracle chemical threat. Having established our perfect natural 3 millimeter shield, how did human innovation in the 1930s accidentally manage to threaten the entire planet? Well, the threat started with a class of chemicals known as chlorofluorocarbons, or CFCs. When scientists first invented them, people hailed them as absolute miracles of modern chemistry. They were incredibly stable, dirt cheap to make, non-toxic, and non-flammable. So naturally, we integrated them heavily into our everyday lives. We use them as refrigerants in our air conditioners and fridges, as the propellants in our aerosol hairspray cans, in foam packaging, and even as heavy-duty industrial solvents. For a while, they really did seem absolutely perfect. But here's the kicker. The very thing that made CFCs so useful to us, their extreme chemical stability, was actually their fatal flaw. Let's walk through this process. Step 1. Because they were so stable, they just didn't break down here in the troposphere. Instead, they survived for decades, slowly drifting upwards. Step 2. Once they finally reached the high altitudes of the stratosphere, the intense, unfiltered UV radiation literally blasted them apart. Step 3. This violent reaction released highly reactive chlorine atoms. And step 4, this is where the disaster strikes. Just one single, solitary chlorine atom can destroy thousands of O3 molecules. It's like a microscopic wrecking ball, essentially eating away our planet's protective shield at a truly terrifying rate. The absolute climax of this whole chemical destruction was something that became globally known as the ozone hole. Now, just a quick clarification. From a purely scientific standpoint, it's not a literal hole where a chunk of the atmosphere just disappeared. It's actually a dramatic, severe thinning of the ozone layer. Because of some very specific atmospheric conditions, this massive thinning was most pronounced over the South Pole in Antarctica. It would appear every single spring, and it absolutely alarmed scientists worldwide. Which leads us directly into section 3, severe consequences of depletion. So what is the actual so what here? What happens when you peel away this UVB filter from our planet? Well, the consequences of unfiltered UVB radiation are basically a cascading disaster. On the human health front, it's the primary cause of malignant melanoma, which is the deadliest form of skin cancer. Actually, studies show that getting excessive sunburns in childhood can increase your risk of melanoma later in life by a staggering threefold. But it doesn't stop with your skin. UV radiation also accelerates cataracts, which can literally cause blindness, and it suppresses your immune system. And ecologically, it's just as bad. It kills microscopic phytoplankton in the oceans, effectively starving the marine food chain from the bottom up. Plus, it significantly reduces both the yield and quality of global agricultural crops. So it was quite literally a threat to our global food security. Let's look at how we fixed it in Section 4, the unprecedented global solution. We were literally staring down an existential crisis. But instead of ignoring undeniable scientific evidence or just getting bogged down in endless political debate, the international community actually responded. The timeline is incredible. Scientists first sounded the alarm back in the 1970s. By 1985, nations came together and signed the Vienna Convention, officially acknowledging the problem. But the real historic triumph came in 1987 with the Montreal Protocol. This treaty achieved universal UN ratification, meaning every single member state agreed to it. It was built entirely on hard science and featured clear, phased timelines. Developed nations were hit with strict deadlines, essentially eliminating the most damaging CFCs by 1996, while developing nations were given the appropriate time and support they needed to transition. And thanks to this sweeping action, we are currently on track for the ozone layer to fully recover to pre-1980 levels by the year 2050. Let me give you a number to really drive this home. Because of this unprecedented global commitment, over 99% of controlled ozone-depleting substances have been successfully phased out worldwide. 99%. Just think about that for a second. We identified a literal global threat. We universally agreed on the underlying science, and we practically eradicated the problem. It is widely considered the most successful international environmental treaty in human history, no question. And the good news doesn't end there. Section 5, the massive climate co-benefit. As if saving the entire ozone layer wasn't enough of a win, solving this crisis yielded an incredible, completely unexpected bonus. Here's what happened. When we phased out those nasty CFCs, industries naturally had to replace them, right? So they initially used hydrofluorocarbons, or HFCs. Now, HFCs were fantastic for the ozone layer. They didn't deplete it at all. However, scientists soon realized they are exceptionally powerful greenhouse gases, contributing hugely to climate change. So rather than start from scratch, the international community just used the exact same successful framework to pass the 2016 Kigali Amendment. This expanded the original mission, legally committing nations to aggressively phase down these extremely potent climate-warming HFCs as well. The sheer scale of this secondary victory is absolutely massive. By simply phasing down HFCs through this Kigali Amendment, it's estimated that we can avoid up to 0.5 degree Celsius of global warming by the end of this century. Let me put that into perspective. In the world of climate science, preventing 0.5 degree of warming from one single policy action is a monumental, genuinely planet-altering achievement. Let's bring it all together now in Section 6, Summary, Solving Global Problems. So, to quickly summarize the core academic takeaways from today's explainer, we now possess a crystal-clear blueprint for solving huge global problems. Look at the track record. We faced the severe threat of CFCs destroying the O3 layer, we implemented the Montreal Protocol in 1987, and we decisively phased out 99% of the threat. Then we faced a secondary threat of HFCs warming our climate. We passed the Kigali Amendment in 2016, and now we're on track to dodge up to 0.5 degree of warming. This simple breakdown proves that decisive, science-driven international cooperation isn't just a nice theory. It yields incredible, highly quantifiable results. So I want to leave you with one final thought today, especially for all the future engineers, scientists, and problem solvers watching this. The story of the ozone layer proves beyond a shadow of a doubt that seemingly insurmountable global crises are in fact solvable. But solving them requires real courage, broad vision, and the actual will to act on scientific evidence. We have the blueprint. We've proven we can do it. The big question now is, how are you going to apply this cooperative spirit to the urgent challenges of today? Things like climate change, water scarcity, and rapid urbanization. Thank you so much for joining me in this explainer today. Keep questioning, keep learning, and absolutely keep solving.